Okay. Being told to review the standard model in 30 minutes is a pretty big charge. So what I'm actually going to do is focus on what one can do to revisit the electroweak constraints at a linear collider. And so depending upon your point of view, I guess I'm going to look at the linear collider from the top down, from bottom up, or from B to Z. This work has been mainly done by everyone but me. These are some of the key players, and I apologize if I haven't listed your name. They've done a lot of nice things. They should get the credit for everything I'm going to describe, and you can blame me for any misrepresentations. So why would we actually want to look at improving the electroweak parameters? Well, I'd like to start with a plot that Sven Heinemeier has made, just looking at the both the theoretical predictions, uncertainties, and the experimental uncertainties in the weak mixing angle versus the W mass. This rhombus shape here is essentially the present theory range. Its uncertainties are dominated by the uncertainty that we have for the top quark mass, and that's along this direction, and in this direction, essentially, the uncertainty in the running of alpha QED up to the Z scale. Then the oval here is the experimental uncertainties that we have on these measurements right now. Now, essentially, if you can do 3 key measurements going to the top TT bar threshold to get the top mass, going to the Z pole, and getting a much more precise sine squared theta effective, and going to W plus W minus threshold to get the W mass, rather than this large rhombus. Essentially, the parametric uncertainties now correspond to one of these small red boxes, where the resolution is now sufficient that you can actually see how the prediction will move as a function of the Higgs mass. And on the other hand, the experimental uncertainties decrease greatly. So this to me is, this plot sold me on this program pretty much straight off. Another way of looking at it in terms of the indirect prediction power is if you have the Higgs mass measured, the W mass you can then predict to about plus or minus 4 MeV, and if you have the W mass, you could predict the Higgs mass to about plus or minus 8%. Now, there's one caveat in this. To really get the sine squared theta effective that to get the constraints prediction power that you'd like, you really also have to improve the running of alpha QED up to the Z scale. And to do that, you really need to improve the low energy R measurements through experiments like PEPN at SLAC, or in the charm region, CLEO-C. Now, first looking at the physics at TT bar threshold, I'm going to focus really on just the top quark mass. I'll mention some of the other things that you can do. And if you're going to talk about a quark mass, unfortunately, you're really stuck about trying to figure out what you mean by the mass. If you do kinematic reconstruction, for example, at CDF and D0, or at Atlas, or even at higher energies at the linear collider, what you're essentially measuring is roughly the pole mass, essentially the position of the pole in the top quark propagator. Unfortunately, that pole mass is really quite ill-defined within QCD. Any of the quarks don't appear as free particles, and you end up with non-perturbative ambiguities of order lambda QCD in trying to actually define what that pole mass is within the theory. And one example of an effect of that ambiguity, for example, is to just try and predict the cross-section in the WW threshold region. And you can see as you go from leading order to next to leading order, blue to green, then up to next to leading order in the calculations, this ambiguity really gives you a big shift, particularly from the next to leading order to next to leading order, and you really don't have what looks like a very well converging series. On the flip side, what you would really like for many of your calculations is a short distance virtual mass. For example, the MS bar running mass for the top quark evaluated at the top quark scale. This is what comes into the radiative corrections and the electroweak constraints. This is what comes in calculating the mass difference in the BB bar or B sub S, B sub S bar systems. Fortunately, the large top width at the the large top width is really a boon in actually trying to extract a well-defined mass from the threshold. First of all, because of the large width relative to lambda QCD, the top quark tends to decay before the TT bar have a chance to form a resonance. So you have no narrow resonance structure. You really have a nice, smooth line shape. And because of other effects, you can actually do a nice job within perturbative QCD in actually calculating the cross-section within this region and getting a reliable extraction of the top quark mass out of it. In addition, there are several short distance mass definitions that you can use near threshold that both give you a nice convergent calculation for the cross-section. Shown here in one of the definitions, you move from the blue to the green and next to leading log, but now the next to leading log is much closer. It's a much smaller correction than we had with the pole mass definition, and you can essentially predict the position of this residual 1s-like resonance peak to about 200 to 300 MeV, which will set the scale of how well you can extract the top quark mass. Furthermore, these masses you can actually relate to the MS bar mass that you'd like in a lot of cases via perturbative QCD scale. So the whole picture is quite nice in terms of using this top quark mass to extract the running top quark mass that you would like in the theory. Now, it turns out that you really need quite a modest luminosity to actually extract the top quark mass from the threshold region. Here's an 11-point scan with 1 inverse femtobarn per point with all beam energy and resolution effects included, and you can get essentially a 40 MeV statistical uncertainty with a very modest cost to a higher energy program. And so overall, from the threshold, you can extract a top quark mass at the level of about 200 MeV, sort of a factor of at least 5 from what you'd expect from measuring the pole masses at hadronic machines. There's a whole wealth of other top measurements that you can make at a linear collider. For example, at threshold, you could measure the total top width. It turns out that the peak cross-section, the peak of that 1s, is essentially proportional to the inverse of the total width. It turns out there's a complementary measurement by looking at the top forward-backward asymmetry that's also sensitive to the width. And kind of the scale is about 100 inverse femtobarns would give you about a 2% uncertainty on the width. And then you'd have to decide precisely how well you want to know the total top width in terms of understanding the top quark contributions in backgrounds to other physics processes, how well you would like to compare the total top width to, for example, the measured partial widths at the linear collider and the LHC to put constraints on new physics. 100 inverse femtobarns is probably roughly equivalent to a snow mass year in terms of the running time. You can also get a handle on the Yukawa coupling at the threshold. For 115 GeV Higgs, there's a noticeable increase in the threshold cross-section. Because of the current uncertainties in predicting that, you would be able to extract a Yukawa coupling to about 20% for this mass Higgs, though the sensitivity will drop off as the Higgs mass increases. At higher energy, you can use this process to actually also extract the Yukawa coupling. It takes a fair amount of data to do it. With an inverse Autobahn up at 800 GeV, you could get about a 6% measurement of it. At 500 GeV, your measurement is going to be roughly similar to the measurement at the threshold. In addition, you can actually extract all of the neutral and charged current couplings of the top quark with a relatively modest luminosity at 500 GeV. You can get most of the form factors at the 1% level. There's a handful where you would extract them at about the 5% level. And the neutral couplings are unique to the linear collider because of the production polarization asymmetry that you can use to extract those. Finally, you're going to be measuring this cross-section to very high accuracy, and that will give you a nice test for doing QCD calculations and electroweak radiative corrections. Turning now to sine squared theta W and the GigaZ program revisiting the Z-pole, I just wanted to give sort of a brief rundown of where we sit with respect to the weak mixing angle, and in some sense it's a little bit disconcerting. If you look at the Z-pole itself, the two measurements that dominate the current value are the left-right asymmetry from SLD and the forward-backward asymmetry for the B quarks at LEP, and these aren't in the best of agreement. Certainly, and I'll mention this a little more later. If you go to lower energy scales, the recent NUTEV result, if you try and compare to these numbers, comes out to be about 3 sigma high. If you go down to even a lower energy scales, the atomic parity violation is about 2 sigma low. And so it's a little disconcerting in terms of understanding how well we understand something that is so fundamental to our electroweak theory. And it would be nice to see which, if any, of these deviations would hold up under a much more precise measurement. So enter GigaZ. And essentially, the idea here is to revisit the Z-pole with a linear collider where, with the luminosity that you expect, you can get about 10 to the 9th Z decays in about a snowmass year. And so you could actually contemplate the interruption of a higher energy program to come back and do the precision measurements over again at the Z. If you wanted to get something more like 10 to the 10th Z decays, that would be a 3 to 5 year program. You'd really need a simultaneous low energy and high energy running to do that, and it would be mainly the heavy flavor program that would benefit, not the electroweak measurements, which will eventually get limited by how well we can control the beam uncertainties. For this program, in terms of polarization, certainly the 80% electron polarization is a given. But here, this is where positron polarization, as we'll see, will be an enormous boon. And there's a real question still of whether that's achievable. If it is, certainly something like 60% polarization would be quite desirable. I'll start off with just mentioning what we could do at a Z-pole scan. These are fairly independent quantities that you would measure with a scan, and you would extract a more precise strong coupling constant. You would be able to improve in the precision of this parameter that essentially normalizes the lepton axial vector coupling, and you could improve the limit on the number of neutrinos species. However, all of these measurements are systematics limited, so you're not going to get huge gains from the statistics here. A lot of it is coming from, with the better detector, getting a factor of 2 improvement in the systematic efficiencies, which would give you a 4 times improvement on the the ratio of the hadronic to leptonic widths, and a 30% improvement in the peak cross-section. But you really need to, while doing this, control the beam uncertainty. There's a potential of controlling it to about 1 part in 10 to the minus 5, which is what you need using a molar spectrometer. This would give you about a factor of 2 improvement in the width of the Z. And then you also need to understand the energy spread and essentially control the Beam-Strelong effects to about 2% of themselves. And really one needs further study of how well we can do this. You may be able to use the Bob collinearity to measure this, though that will put very stringent demands on your detector alignment. You might be able to use a 5-point rather than a 3-point scan to limit this. If you can't control this, then the width and the axial vector normalization will essentially be limited by those numbers. And then the Z mass will not be remeasured. In fact, that will tend to set the energy scale at the linear collider. Now, in terms of extracting sine squared theta w, it's really the left-right asymmetry that's the variable that's most sensitive to it. And you can define the left-right. The left-right asymmetry is just the difference over the sum of the number of z's from the left and right-handed polarized beams, and you can relate it this way to an effective sine squared theta w. The measurement of reference here is the SLD measurement, since that was the only polarized Z experiment, and GigaZ will have about a factor of 2,000 times the SLD statistics. Now, in terms of the electron polarization, if you have no polarization at all, essentially in the end it will be the absolute polarization uncertainty that dominates the measurement. The experts seem to think that 0.25%, given the SLD experience where they got 0.5%, is quite feasible. And if that was the limiting uncertainty, you would go from 0022 on ALR to about 410 to the minus 4, a factor of 5 improvement. If you have the positron polarization, you can then use the Blondel scheme where you combine the number of Z's that you obtain in all 4 helicity combinations. You essentially get an effective 95% polarization, and with this scheme you don't need the absolute polarization measurements. And that would allow you to extract delta ALR to 10 to the minus 4. Even if you had only 20% positron polarization, that would correspond to being able to get down to 0.1% on the absolute electron polarization if you had just electron polarization. Now, in terms of what you need on the polarization, you still must keep control of the relative left-right polarizations at the order of 1 part in 10 to the minus 4. The experts seem to think that this is quite feasible. If you are trying to keep the absolute polarization measurements down at 0.25%, the SLD experience really suggests that you'd like to have the polar emitters after the IP so that you can measure beam-beam effects on the polarization. But that's, of course, difficult without having a crossing angle, as we heard earlier this morning. Another question is whether the positron helicity, if you've got positron polarization, can be switched rapidly enough relative to the stability of your beam conditions so that a lot of the systematics will cancel naturally. And we don't even know what the relevant time scale is, let alone whether we can switch rapidly enough. So those are open issues that we need to investigate. Another effect that one has to contend with is the fact that the left-right asymmetry that you measure will change quite rapidly away from the Z-pole because of the Z-photon interference. So again, you need to control the beam energy scale to about 1 part in 10 to the minus 5. And you need to control the Beam-Strelong at that level as well. Well, to a few % of itself, but so that you know the effective root S shift. Now, if you can use the same beam parameters that you used in the scan, you essentially normalize most of that away. But if it turns out that you need different beam parameters at the peak, then you really need to do a good job on this. At Tesla, for example, if you completely ignored the Beam-Strelong effect, you'd end up with a shift that's a factor of 9 bigger than you hope to measure. Now, one thing that you could do is trade off luminosity for reducing the Beam-Strelong. With the NLC, you could take the expected shift of about 130 MeV down to about 20 MeV with about a factor of 5 penalty in the luminosity. At Tesla, the numbers are more like 40 MeV going down to essentially nothing for a factor of 5 penalty. If those beam issues can be controlled, then you really end up with a very nice measurement of sine squared theta W, essentially a factor of 15 more precise than we currently know it. One also wants to go back and reinvestigate the ZBB bar vertex. Again, there's in the B asymmetry, there's something like a 2.5 to 3.5 sigma discrepancy with the standard model that persists. R sub B is now completely consistent with the standard model. So in some sense, you could look at it as the axial vector coupling seems to be in good shape, whereas with the B asymmetry, it maybe is suggesting that the vector coupling has a problem with it. These are statistics-dominated measurements, so it's a little surprising to get such a big discrepancy, but we'll have to see how things sort out, and it will be interesting to see if this persists with the increased statistics. With GigaZ, you would expect essentially a factor of 5 improvement in R sub B from the improvements in B tagging, and with the improved luminosity, improved polarization measurements, either get a 6 times improvement with no electron polarization, but the 0.25% absolute polarimetry, or if you do have positron polarization, you get about a factor of 15 improvement in A sub B. So this current blue circle shrinks down to the red. Now, certainly LEP and SLD have both made a lot of contributions to B physics, so it's worthwhile just looking at what the B physics contributions from GigaZ could be. Certainly there's great potential, particularly with the production flavor tagging that just comes from the forward-backward asymmetry of the B quark production with the polarized beams. Your statistical sensitivity essentially scales with the product of efficiency times the dilution factor squared, where the dilution factor is 1 minus twice the mistag rate. And whereas hadronic and the B factories have values in the range of 0.1 up to 0.25 or 0.3, this forward-backward asymmetry really gives you a big boost, and you can reach values of about 0.6, which would be very nice. There's also large B boosts, so the Bs are well separated, and you can do very nice B tagging, clean B tagging, and you have a well-defined initial state, so you can really do neutrino reconstruction quite well, which has been used quite effectively by LEP. However, you do have stiff competition from the B factories, from L8CB, from BTEV, and if you just look at these standards, such as sine 2 beta, sine 2 alpha, you really are just doing cross-checks of some of the other measurements. For example, with the sine 2 beta and sine 2 alpha, you'd essentially get within about a factor of 2 of the uncertainty on the of the hadronic machines. However, there are some unique opportunities that GigaZ would give you. For example, if you're trying to extract VCB or VUB from inclusive measurements, right now there are completely uncontrolled theoretical uncertainties from quark-hadron duality violations in the predictions of the inclusive rates. However, the B sub S system would be affected much differently than the B sub U or B sub D systems by the duality violation. And so if you can get consistent measurements of VCB, for example, in both the B sub U and the B sub S systems, then you can really start to limit how big an uncertainty you have. Another nice feature is that you can produce polarized lambda B decays, and you can use these, for example, to probe this coupling of in B to quark gamma decays, which would, for example, a left-right symmetric model would give you contributions here, whereas the standard model only gives you contributions here. And beta S gamma measured from B factories, even in the presence of the left-right model, would only probe this coupling. And it turns out with 10 to the 9th Z's, you actually get quite an interesting reach in limiting this kind of coupling. GigaZ may also be about one of the best places to actually try to measure B going to X sub S nu bar. This will be affected quite differently than X sub S L plus L minus from non-standard model of physics. The question is, we still don't know what the reach is or whether we control the beta tau nu background. So this is one area that some study is needed. This may also be one of the best places to get an initial handle on the production flavor tagged B0 to pi 0 branching fractions, which you would like to use in the unitarity triangles for extracting the sine 2 alpha measurements. Finally, going to the WW threshold to extract M sub W, I'll mention again that the potential indirect precision on extracting the W mass is about 4 MeV, so it would really be nice to improve on the 15 to 20 MeV precision that you could get at the Tevatron or LHC. And the question is whether the linear collider could approach such a precision. Once again, it turns out to be the beam energy scale and the Beam-Strelung effects that will be the most serious issues. And in terms of the direct reconstruction of the W mass at high energies, one needs a beam energy constraint. And given that you're going to be scaling up from the Z mass, most likely, and also that given the scaling of the Beam-Strelung, it may turn out to be much more desirable to look at the threshold region to get a precise W mass. So, but even at the threshold, it turns out that the E-beam and the Beam-Strelung control you need are a big challenge. Again, you need the beam energy to about 10 to the minus 5. You can potentially monitor this by using radiative returns to the Z and looking at Z to mu mu and EE. Certainly, the integrated statistics, this would work. The question is, are there sufficient statistics for studying the square root of S as a function of time using this technique? And that's something that we need to address a little more clearly. With Beam-Strelung, you need to control this distortion of the shape in the threshold region to about 0.12%, which would then correspond to plus or minus 2 MeV uncertainty on the W mass. And it appears that one can use the Baba ecolinearity to control this, but again, one needs to, this places stringent demands on detector alignment. Finally, a fair amount of work also has to be done in theory, getting the cross-section shape, again, down to 0.12% so that you're not really blowing yourself out of the water with the theory uncertainty. You don't really need to get the absolute scale to this level, but you do need to understand the shape at this level. And I guess in particular, trying to deal with the finite width of the W is really a challenge. But we've got a few years. If you can control the beam-related uncertainties, Graham Wilson has done a very nice job of showing that the rest of the experimental issues are essentially under control. If you, again, devote about 100 inverse femtobarns of data to a 6-point scan, again, given 60% positron polarization, you can get about a 5 MeV statistical uncertainty from the scan. This is his optimal scan showing the optimal distribution of points. And essentially the strategy is that at threshold, the T-channel neutrino exchange diagram dominates. And so you can control the backgrounds by roughly turning off the WW production using other helicity combinations to essentially constrain the polarization measurements. In terms of the polarization measurement that you needs, 0.25% absolute would essentially give you the precision that you needed. If this becomes difficult, you could again use radiative returns plus the Blondel scheme without significantly decreasing the uncertainty in the W mass extraction. So if all is said and done, it appears that if you can control the beam-related uncertainties, that you could get down to about a 7 MeV uncertainty in the W mass. But you'd really want to make sure that you can indeed control the energy uncertainties there before you devote about 10 to the 7 seconds in this region. I'm running out of time, so I'm not going to go through this table. It lists for reference, you can look up the relative reach. I would like to mention some of the constraint potential that you would get using GigaZ. For example, if you go to the paper that Michael mentioned this morning, they go through and analyze, essentially, they've surveyed models with a heavy Higgs where you may not see it at a linear collider, you may not even see it at the LHC. And what they generally find is that you get significant deviations in S&T from the standard model that would be observable with the precision that you'd get from GigaZ. For example, with the Technicolor models, you expect S&T values that are greater than approximately 0.1. This ellipse up here is centered at about 0.11, 0.11. And so you would end up with essentially a 5 sigma standard deviation given the GigaZ and top threshold measurements. Whereas even with the LHC values, the limits would be significantly degraded. Sven also mentioned the constraint potential with SUSY, and he walked through this plot. I just want to mention a little more, or reiterate, essentially, that there are various constraints that you can use within the MSSM in addition to, well, that are similar, essentially, to the standard model constraints. For example, within the MSSM, you can again do the sine squared theta W versus W mass constraints, predicted versus measured values, just as I showed for the standard model at the beginning of the talk. MH becomes a predicted quantity within MSSM, so this gives you one more constraint. And Sven walked through the example of being able to constrain the mass of the heavy scalar top much more effectively at GigaZ than you could at the LHC or with just a non-GigaZ program at the linear collider. So in conclusion, I really think that the low energy program adds great value to the overall linear collider and to the general HEP program. It gives you much more powerful constraints that are useful for self-consistency checks, for interpretations of new particles. It gives you much more effective mass reach through radiative corrections, and the tighter you can get those constraints, the better. And unique flavor physics contributions would come along as a bonus. Really, it's the beam energy and polarization issues that we need to further study. All of the solutions are going to involve monitoring instrumentation. It's clear from Tom's talk this morning that People are beginning to address getting that instrumentation in there, but we've got to make sure that there's sufficient monitoring in the baseline design because it's going to be really hard to retrofit. Thanks.
Remind those people here who are LEP collaborators. Olive has done an attempt to get the LEP2 energy scale from the return to the Z. And the results are disappointing. They disagree with the LEP standard by, if I remember correctly, 4 sigma. And it seems really important to me that someone should find the resolution of this problem before the LEP data is archived and forgotten.